तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we discussed transconductance type multiplier using what is called translinear principle. The voltage Vx was converted into a sort of linear differential current using a transconductor of this type. The current here was I naught naught by 2 plus Vx by Rx, and here I naught naught 2 by 2 minus Vx by Rx. Differential current of this type was flowing here, and that was the current in the diode. And we saw that the current in these transistors, which we called as T1, T2, T3, T4, were respectively, let us say IC1, IC2, IC3 and IC4. These were the currents, and these currents were related to this in the following fashion, that this current into this current, because in the clockwise direction, right, and anti-clockwise direction, the current products should be equated. This current, which is I naught naught by 2 plus Vx by Rx, divided by into this current, that is IC2, was equal to I naught naught by 2 minus Vx by Rx into IC1. And since this was this voltage, these two voltages are adding, so I naught naught by 2 minus Vx by Rx into IC1, and the same voltage is also applied to another set, and therefore what we get is that I naught naught 2 by plus Vx by Rx into this again is going to be coming like this, and then here, so into IC3 equals I naught naught 2 minus Vx by Rx into IC4. Using this relationship and also the fact that IC1 plus IC2 equals I naught by 2 plus Vy by Ry. Here this is I naught by 2 plus Vy by Ry, and this is I naught by 2 minus Vy by Ry. Again, that means IC3 plus IC4 is equal to I naught by 2 minus Vy by Ry. We could establish ultimately that V naught, the differential output voltage taken here, is going to be product Vx Vy divided by Pr. Okay. So, this we had shown in the last class. Right. This Vr could be made equal to 10 volts by proper choice of Rx, Ry and RC2 and I naught by 2 and I naught by 2, right. So, we can make VR equal to 10 volts, okay. By proper Rx can be made equal to Ry, okay. Rx can be made equal to Ry, and we have here this I naught can be made equal to I naught naught. So, that all these current sources can be derived out of the same current mirror principle. So, I naught can be made equal to I naught naught. Okay. What is the expression in terms of Rx RNA? Can you give me this? Vx Vy Rx Ry I naught naught into RC2, right? 4 here, yeah. So, we can select Rx equal to Ry equal to 2 RC2, okay, equal to R. Then what happens here is this is equal to Vx Vy Rx equal to Ry equal to 2 RC2, 1 Ry gets cancelled with RC2. So, we get R, okay, I naught naught by 2, okay. So, this R I naught naught by 2 is made equal to 10 volts, okay. Therefore, this becomes equal to Vx Vy by 10 volts. Now, once we select this value, we can see here that this becomes equal to 0 under the worst condition when Vx max becomes equal to I naught naught by 2 into Rx, and we have already chosen I naught naught by 2 into Rx or R equal to 10 volts. So, this can now take care of Vx and Vy less than or equal to 10 volts as the dynamic range greater than or equal to minus 10 volts automatically, right. So, this design will see to it that this multiplier will function linearly in the range minus 10 volts to plus 10 volts automatically the moment we select the components in the above manner. Okay. Is that clear? So, this multiplier therefore is useful for us within a dynamic range of minus 10 volts to plus 10 volts, and V reference is 10 volts. So, it can give you at most plus minus 10 volts as the maximum output, because Vx equal to 10 volts, Vy equal to 10 volts. Then since Vr is also 10 volts, V naught maximum also is plus minus 10 volts magnitude is going to be maximum of 10 volts. So, this transconductance type multiplier is a precision multiplier which can be basically used up to about 1 megahertz very easily. Now, this IC multiplier is readily available for use in a variety of applications. Okay. We will therefore go into application of precision multiplier and then go back to further types of multipliers at a later date. Before we start discussing about other types of multipliers, we can digress and go to applications. It is obvious that the transconductance type multiplier is the one which is used in a very large number of communication applications, and therefore, it is time that we discuss some applications and then go back to discussion of other types of multipliers. Now, the multiplier, the ideal multiplier that we had designed, Vx, Vy and the output V naught, let us say, is equal to Vx Vy by 10 with a dynamic range with all the offset and feed through being adjusted to 0. Okay. This is the ideal multiplier. Let us therefore discuss the applications and see where in what are the areas this is of importance. First and foremost, let us consider V y is equal to a constant DC voltage V c, which is called the control voltage, and V x is my regular input V I. Then output V naught is going to be, this is the application A, as a voltage controlled amplifier. Voltage controlled amplifiers find a variety of application, particularly in music synthesizers and AGC, AVC, etc. schemes, automatic gain control scheme, automatic volume control schemes, amplitude stabilization of oscillators. In all these things, voltage controlled amplifiers are needed. So, V naught then equals V c by 10, which is the gain, into V I. This is the gain of the amplifier. Gain in the sense we know that it is not really voltage gain that we are talking of, it is power gain, right. So, this still is an amplifier. V c is always less than 10 volts. So, the gain is always less than 1 in this case of ideal multiplier, please, but V c can take on both positive and negative. So, it can become a non-inverting amplifier or inverting amplifier depending upon the sign of V c. So, this is a voltage controlled amplifier which can give you an inverting type of amplifier or non-inverting type of amplifier, and the gain can be varied all the way from 0 to 1 linearly. Okay. Next, if such a voltage controlled amplifier is there and I use this in combination with, let us say, an integrator, let us see what happens. The normal integrator has the input here, but now I am feeding it the input through a multiplier. This is V I and this is V c. So, obviously, this becomes V I V c by 10. So, output now becomes integral, therefore, V I V c by 10 R c into S, okay, with a negative sign. Normal integrator output is minus V I by S C R. Okay. So, now it becomes minus V I by 10 into V c, okay, by R C S. So, it is equivalent to saying that it is like earlier integrator, but with the time constant R c being replaced by R c, okay, into 10 by V c. So, the time constant is changed from original R c into R c by V c into 10. So, the time constant is inversely proportional to V c. If that is the case, if I design an oscillator, for that matter filter or oscillator using this, then the frequency of oscillation or the pole frequency of such a system is going to be 1 over R c under normal case, going to be replaced by V c by 10 R c. We had earlier discussed KHN filter or universal active filter, okay, which use two integrators. Both the integrators now, let us say, are replaced by such modified integrators. Then the omega naught or the pole frequency is going to change to V c by 10 R c. If you design a double integrator or quadrature oscillator, the frequency of oscillation or the natural frequency of the system also is going to be 1 over R c, which is going to be replaced by V c by 10 R c. So, that means I can build voltage controlled filters, okay, voltage controlled oscillators linear, okay, all this using such a replacement of the integrator. So, wherever ordinary integrator is there, you replace it by a multiplier in combination with integrator, then the RC time constants will be replaced by 10 RC by VC, and all such circuits become voltage controlled, and they can be used again in music synthesizers, okay, programmable filters, okay, and all these things. Voltage control oscillator, voltage controlled oscillator is again a circuit whose frequency of oscillation is directly proportional to the control voltage, and it is nothing but an FM generator. Because if I now feed a carrier frequency here plus a modulation frequency, if I feed this here, right, as a voltage, right, then actually modulating frequency is fed here, right. So, output will be a carrier frequency plus the quiescent frequency, which is quiescent frequency plus modulating frequency, which is nothing but an FM. So, voltage controlled oscillators are nothing but FM generators. This is a linear thing, and therefore, it is a wideband FM generator. Okay. This is important, that because of its perfect linearity, it is possible to use it for wideband FM generation. In things like, let us say, frequency shift keying, okay, etc., such FM generation is FSK generation is possible. Apply the digital ones and zeros here, okay, digital ones and zeros with additional DC, then output will be, okay, a quiescent frequency plus the frequency varying from a certain value, let us say at 200 hertz it is 1, at 100 hertz it is 0, something like that. So, you can get an FSK output directly from this. So, voltage controlled amplifier, how this is suitable for use in let us say AGC and ABC, we will discuss slightly later, right, because it is going to be a control system like that of a voltage regulator, we will discuss slightly later. Other applications like, now if Vc Vx is equal to, let us say, Vp sin omega 1 t, Vy is equal to, let us say, Vp1 Vp2 sin omega 2 t. The inputs are now different. These are two different frequencies that are coming as inputs to the multiplier. So, what is going to be the output? This is of interest to us in communication. So, output is going to be Vp1 sin omega 1 t, Vp2 sin omega 2 t divided by 10, which is going to be Vp1 Vp2 by 20 times sin A sin B is cos, that is by 2 is there, factor of 2, cos A minus B, which is omega 1 minus omega 2 t minus cos omega 1 plus omega 2 sin A sin B is equal to cos A minus B minus cos A plus B by 2. This is known to you. So, these are what are called side bands. If omega 1 is the carrier, and omega 2 is the modulating frequency, omega 1 is the carrier, omega 2 is the modulating frequency. This output communication engineers call as double side band system. Carrier is absent, this is called double side band. It will have omega c minus omega m and omega c plus omega m. So, in power efficient designs, you do not want to unnecessarily send the carrier, you just want only the side bands sent, and you can receive at the receiver end the modulated output and detect the output. By putting an antenna whose bandwidth is sufficient to receive omega c plus or minus omega m max, you can receive this information and then put it in what is called as a mixer. So, this is nothing but a DSB modulator. Multiplier is nothing but a DSB modulator. When Vx and Vy are respectively two sine waves, one is the carrier, another is the modulating frequency, then it is called a DSB modulator. This is the second application that we are discussing. Now, if this is received at the receiving antenna and let us say omega 1 is omega c plus or minus omega m, that is one input is the DSB itself and omega 2 is let us say omega c, let us call this minus omega if, omega c minus omega if. This is called local oscillator frequency. Because omega c is a fixed frequency, omega if is another fixed frequency. What happens? Let us see. Again, we get this plus this, and this minus this. So, we see that the output will correspond to 2 omega c plus or minus omega m minus omega if, this plus this, and this minus this omega c will get cancelled, get omega if plus or minus omega. So, when you mix this, it is called a mixer. You are mixing these two frequency components, it is called a mixer. What is a mixer? Again, it is nothing but a multiplier. Only thing is the input is different now. One is a DSB modulated input, another is the local oscillator which is having a frequency omega c minus or plus omega if, it does not matter. So, this local oscillator frequency is mixed with incoming frequency and you get omega if plus or minus omega m and this. You have to isolate this from this. So, you put a band pass filter whose center frequency is omega if, with a bandwidth sufficient for omega if plus or minus omega m max. This gets eliminated, this is a very high frequency component. So, this gets eliminated and you have now transferred the wanted information which is plus minus omega m from the carrier to if, which is a lower frequency. This is what is done in both television as well as radio receivers, so that the amplifier design becomes very simplified. Amplifier that is designed to amplify all the signals have to operate at a fixed frequency, called intermediate frequency, then the amplifier design is very simple. So, mixer is the name attributed to the same multiplier whose input is changed from the original carrier and modulating frequency to modulated frequency and local oscillator frequency. Now, we will see how it also gets the name of, let us say, detector. The same thing is going to be called, okay, modulator, mixer or detector, simply based on inputs and output structure difference. So, the multiplier is a basic component which is involved in communication again and again, right, as a mixer, as a modulator or as a demodulator. This is called what is this? Now, we have information in omega IF plus or minus omega IM. I put a local oscillator whose frequency is omega IF. So, output will be twice omega IF plus minus omega M and omega M. I can now eliminate omega IF plus minus omega M by using a simple low pass filter, right, whose cutoff frequency is, okay, something higher than omega M max. Okay. So, I just put a low pass filter, it will remove twice omega IF plus or minus omega M. Okay. The input therefore is the IF output and an IF local oscillator frequency. Then it detects the modulated frequency, that is called a demodulator. This is also called balanced modulator and this is balanced demodulator. Okay. This kind of thing, receiver design, is possible only when at the receiving end I can generate in the local oscillator a frequency which is as stable as that has been transmitted, that is omega C, okay, minus omega IF should have the same stability. Not, it can be good or bad, but if the stability of transmitter is good, right, this could be as good or as bad. Okay. It should be tracking with that, otherwise there will be problems in receiving. Same thing is true with this detector, that I should be able to generate a local oscillator frequency which is omega IF, okay, with same amount of stability as that of the omega IF strip itself. Okay. So, with that requirement, the receiver design becomes pretty complicated. That is why it is not normally used in the common cheap radio receivers called super heterodyne receivers, which make use of a different principle altogether in modulation, that is called amplitude modulation as against DSP. What is an amplitude modulator? This we can learn from the fact that an amplitude modulator AM circuit is nothing but a multiplier. Okay. Let us say Vx is Vp sin omega Ct, Vy on the other hand is a DC, okay, plus Vp2 sin omega ft. So, that when you multiply, there is, apart from the product component which is omega sin omega Ct into sin omega mt, you have DC multiplied by the carrier, which will give you sufficient carrier to identify the signal properly. This is called, therefore, this is nothing but a non-ideal multiplier, where you have the x feed through component coming. See that this is nothing but a non-ideal multiplier, where x feed through component is coming. It is not just the product component. So, if you have a non-ideal multiplier, you can obtain an amplitude modulated signal. What is the advantage of amplitude modulated signal? As against the DSP, okay, you can detect this simply by envelope detection, which is done simply by using a diode. So, the amplitude modulated signal, which looks like this, that is the envelope, and the envelope contains the full information. Therefore, you can chop this off using a diode and then put a filter so as to detect only the envelope. So, that detector is a very simple detector, does not require generation at the local oscillator frequency which is as stable as that is not transmitted. So, this is AM generation. That means, AM generation is also possible with the same multiplier. Only thing is that multiplier need not be an ideal multiplier, it can be a non-ideal multiplier with X feed through or Y feed through component. Next, the communication application, we have another important application wherein the frequencies are the same, but the input can be now Vp sin omega t, this is Vx and Vy is Vp1, let us say Vp2 sin omega t plus phi. Once the frequencies are the same, there can be a phase difference. So, if you feed this as the input x and y, what will you get? Again you will get a component which is Vp1 Vp2 by 20 cos omega 1 minus omega 2, here it is this minus that is cos phi minus this plus this, that means cos 2 omega t plus phi. This is the output. You can now see that by putting a low pass filter, I can get rid of this and output is Vp1 Vp2 cos phi by 20. What is phi? Phi is nothing but the phase difference. So, this is a phase detector, an important building block in a variety of applications, right? Phase detector. It is not linear, it is non-linear because output DC voltage is proportional to cos phi, not phi. You can make it linear by simply passing these waveforms through comparators or limiters, what are called as amplitude limiters. So, if you for example pass it through amplitude limiters, output amplitude of Vx is let us say limited to some value. So, this is 2 pi, this is pi, and the other waveform is let us say relayed from this waveform by a factor of phi. Let us say the amplitude to which it is limited is plus Vs and minus Vs. This can be done by making these voltages go through comparators, right. So, the amplitude will be limited to supply voltage plus Vs and minus Vs, both of them. So, Vx and Vy get fed through this, and then to the multiplier. So, what will be the output? Here when this is positive, this is negative. So, output is negative and in this region it is Vs squared by 10 negative, and in this region both are positive. So, output is positive Vs squared by 10. Again here it is one is positive, another is negative, again it is minus Vs squared by 10. Again here both are negative. So, it is positive Vs squared by 10. So, in one cycle of this waveform, right, this goes through 2 cycles, that is what it says in this multiplication also. There is a 2 omega t component coming into picture. Apart from that, if you actually evaluate the average of this, now if this is let us say phi, the average of this is going to be minus Vs squared by 10 into phi, this into minus Vs squared by 10, and this period is pi minus phi, right. So, plus Vs squared by 10 into pi minus phi. and since it is getting repeated in the same manner, right, it is enough if we take the average this way and divide it by total of pi itself, right. If you take the average for 2 pi also, it will be the same average, right. So, you get this here V average as being equal to V s squared by 10, okay. This pi and pi get cancelled, 1 minus 2 phi by pi. You can see that the average DC component is directly proportional to phi. So, this becomes a linear phase detector. Right. So, you can see that in communication engineers call these amplifiers as limiters, not as comparators. Okay. You can limit the amplitude by using high gain amplifiers, okay, and apply this to a multiplier, which is nothing but a modulator or mixer or anything. But if the two frequencies are the same, then the average component at the output will be directly proportional to phi. This is called a linear phase detector. Therefore, we can use it as a linear phase detector in we will see this is a basic building block of a phase lock loop also. Later on we will see this. Here this point that it is proportional to cos phi can be exploited in using it for power measurement. If Vx is proportional to line voltage, that means you put a voltage transformer there, then Vy is proportional to line current, then you put a current transformer. Okay. The output of the voltage transformer and current transformer you apply directly to the multiplier, and you put a low pass filter, you will get the power factor directly. The output voltage will indicate the power factor. Okay. If you really use the amplitude information, it is nothing but the power, okay, consumed in the line. You can use this information as a direct replacement of what is called 2 wattmeter method of power measurement. The 2 wattmeter method of power measurement in 3 phase circuit, okay, can be translated in terms of 2 such multipliers being used, okay, in order to evaluate the power of the 3 phase circuit. Okay. So, it can be used as a wattmeter. Phase detector, wattmeter. Now, you can see that instead of taking this as the output cos phi, this can be eliminated by using a high pass filter. Only this can be taken. What is this going to give us? You have put omega as the input, you have got 2 omega as the output. This is called frequency doubler. This output, when I select only the high frequency component, reject the DC, is called frequency doubler. This is very important in its application of generating stable high frequency components from stable low frequency components. Let us say it is very difficult to generate stable high frequency component, then you have to synthesize such frequencies by doubling or tripling or multiplying. So, for frequency multiplication this can be used. If you can double, you can triple, because this can, the doubled frequency can be in one input, and again omega can be the other input, 2 omega and omega, you will get 3 omega. So, like that you can multiply frequencies. Okay. So, frequency synthesis, this can be used. If you can use it for frequency synthesis, I can get omega, 2 omega, 3 omega, etc. Then I can generate the harmonic components, and I can therefore obtain any periodic waveform, okay, using a periodic waveform as the input. Okay. A triangular waveform, for example, can be used as the input. Triangular waveform is nothing but x or t. So, using this input I can generate a sine waveform, okay, which is going to be t minus t cubed by factorial 3 so on, right. So, we can generate a periodic waveform of any shape using a triangular waveform using this kind of frequency synthesis. Other applications of the multiplier, like how to use it as a divider. We have seen that in the log anti-log multiplier we can use it straight away as a multiplier or divider, whereas this transconductance multiplier, the output is Vx Vy by 10, straight away a DC, which is generated using a DC current and a resistance. Right. So, we cannot possibly use it as a divider straight away. How to convert a multiplier into a divider? So, this multiplier can be put in the feedback path. This is always the case. I have been repeatedly telling you that if you have a certain function, the inverse of the function can be always obtained by putting that functional block within the feedback loop of an op amp. So, let us consider an op amp of this type. So, this is, let us say, V I, this is V naught. If this is V I, this should be V I if the feedback is negative in the case of an op amp, and that is straight away equal to, let us say, this is V I 1 and this is V I 2. So, this is V I 1. So, and that V I 1 is equal to V naught V I 2 by 10, V naught V I 2 by 10, because this is going to give you Vx Vy by 10, V naught V I 2 by 10. So, we see here that V naught is going to be equal to 10 V I 1 by V I 2, which is nothing but a divider. Now, a word of caution, because this is going to be a divider only when V I 2 is remaining positive, because if this control voltage is positive, this gain is positive, you remember. If this control voltage is negative, the gain, it will be acting as an inverting amplifier, we have to say. For this feedback will become positive feedback if this is negative, right. So, this is valid as long as V I 2 is positive. So, this particular thing is working satisfactorily for V I 2 greater than 0. Okay. Is that point understood? If this is positive, the phase, there is no phase inversion between this and this. If this is negative, there is a phase inversion. If there is a phase inversion, this there is negative, okay, already 180 degree, this again 180 degree, there is a positive feedback, and this circuit will fail to function. So, this is the limitation of this circuit with negative feedback. It cannot work for any polarity of your voltage that you are considering. Now, this also can be used for squaring. How do you do squaring? Squaring you do simply by connecting both the inputs to the same thing, Vx and Vx. So, output will be Vx squared by 10. But we would like to do square rooting, let us say. Square rooting, how do you do? So, square rooting can be done by simply connecting again this squaring circuit in the feedback path. So, instead of this still remains the same V I 1, this is V I 1, okay. This is now Vx and Vy both are equal to V naught squared. So, Vx and Vy are equal. So, multiplication this will result in V naught squared, or we get now V naught squared by 10 is equal to V I 1. Okay. or V naught is equal to root of 10 into V I 1. So, this is this. So, here the essential thing is once again this V I 1 okay, has to be always positive. If it is negative, once again we cannot get an output. What does it mean? That means actually speaking that V naught here has to be always positive. Okay. Otherwise, there will be the sign change is not recognized here, because this is a squaring circuit. Okay. Whether it is positive or negative, you will get the same output. Okay. So, this is a square rooting circuit. If you have a square rooting circuit, okay, you can do so many things. Squaring and square rooting we know. What is called as true root mean square value. Root mean square value, RMS value of a given waveform, periodic waveform. How do you true RMS value? How do you find out that? By definition, you will take square, suppose it is V, you take square of V and then mean, that means integrate, okay, and then root, square root. Okay. So, integrate over, let us say it is a time period, okay, that is the averaging. So, what do? You put a squaring circuit which is nothing but a multiplier. This is V. So, you have got the square, then the averaging circuit, that means you will take the average, you can take RC time constant. This is nothing but a low pass filter, right, that will do the integration, right, averaging circuit and then square rooting, right. This averaging is a DC, okay. So, you will now take the square rooting of that. So, this complete circuit is nothing but a very useful tool called true RMS root mean squared indicator, right. So, the entire thing can be built using multipliers. Such units are available in the market for finding out the true RMS value of a given waveform.